talk about USB DFU mode. Travis was an early hacker who ended up on my couch when he became homeless in Montreal and made it across the border via mechanisms that probably would not work these days, and ended up camping out and teaching me that USB, no matter how many endpoints it said it had or what should be master and which should not, that it was really just a bus. Oh. And I think we're about to see that come back. So without further ado, Travis.
Howdy, y'all. Today we're going to talk about the USB device firmware update protocol. And we also have a tool release. If you want to photograph this slide, I've got the URL here. For those of you under 30 in the audience, URLs is what we used before QR codes. And if you type this in, it'll get you the source code. And then if you're like over 35, this is the Unix command line thing, so you don't have to open your browser either. My name is Travis Goodspeed. I have a couple of past projects that you might have heard about. The International Journal of Proof of Concept, or Get the Fuck Out, is one that I've been working on for many years now. And more recently, I have a book called Microcontroller Exploits. The purpose of microcontroller exploits is to tell you how to break into a microcontroller when the chip itself is locked, you do not have read permission, you are not supposed to read it, but you want to read it anyways. And as soon as you get past that readout protection, you get a memory dump of the chip, and everything becomes a software problem. You're no longer dealing with hardware, you're just dealing with an IDA Pro project. I also make a CAD program called MaskROM tool. It is a Qt6 application for taking a photograph of the read-only memory in a microchip and working your way backward to the logically ordered bytes and disassembly of that program. MaskROMs are great because they're physically made by one of the masks in manufacturing the chip, and they cannot be patched or upgraded except by doing a mask revision, which is very expensive, and then manufacturing new chips, which means that your old warehoused chips are, they have to be thrown away. I also make an assembler called GoodASM. It is symmetric, so you make one definition and you get both an assembler and a disassembler, and it's designed for you to add a new assembly language as quickly as possible. So you can sit down in a coffee house and in an hour or two, you can implement any of the 8-bit CISC instruction sets that were popular in the 80s and the 90s. And then MD380 Tools is a project of mine where we took an off-the-shelf push-to-talk ham radio, exploited the bootloader to dump the firmware and the firmware encryption keys. And having those keys, we were able to reverse engineer the firmware and replace the Chinese font with new code, written in C that did all sorts of fancy new features. When I was exploiting the MD380, the handheld ham radio, my exploit uses the USB device firmware update protocol. And it bugged me while writing this up for my recent book on microcontroller exploits that I knew how to exploit DFU, but I kept finding myself writing crummy Python code to do it. And I would much rather have like a scriptable Unix command line tool that implemented all of the different things I might care about so that I could quickly exploit a newly discovered chip, dump its firmware, and then move on. If you want to play around with this software, you need some hardware that it's compatible with. My buddy Ozzy sent me this. It's labeled as if it's an STM32, but it's actually a counterfeit called the APM32. You can identify that it's a counterfeit either by boiling it in acid and looking at the microchip, or by the USB device firmware update protocol. It freely tells you over USB that it's counterfeit. And if you checked for that in your manufacturing line, you would be able to identify that this is not a real chip. Well, it's a real chip, but not the chip that it pretends to be. And this is important because with laser remarking, you might accidentally buy thousands of the wrong chip and have to choose between substituting it or stopping your manufacturing line. I don't know how many of you work in manufacturing, but every time I, as a security guy, have told the manufacturing guy that I'm shutting down his line, he has a very bad day and some very colorful language for me. You can also grab an MD380. These are toward the end of their life, so you might get the VHF version instead of the UHF one. And I'll warn you up front that I am no longer enthusiastic about my project for this. The code is open source, but I quit development on it, and I'm no longer adding new features. If you add a new GitHub issue suggesting a feature, you can rot in hell because I will not implement it. If you mark up a bug, someone else might fix the bug, and I might merge that. What MD380 tools lets you do is it takes the manufacturer's radio firmware, this is for a digital push-to-talk radio, and it patches it to add new features and new menu items. These radios speak a protocol called DMR. It's also known as Moto Turbo. A lot of university police departments use this. This is not P25 that fancier or more regional organizations might use. Amateur radio made use of this as the first popular digital protocol for amateur radio, but this was designed for business and police use. And one of the big differences is that in ham radio, I want to hear whatever is on the channel at the time. In a business radio, I don't want to hear anything that is not intended for me or a group that I'm a member of. So when we were using amateur radio with the digital radio practices, we had this problem that people would transmit over each other because they wouldn't hear that the channel was already in use. And to make this worse, the radio has two time slots. It's TDMA, time division, multiple access. So it's completely cool for me to talk on time slot 1 and for you to talk on time slot 2. But it is not cool for us both to talk on time slot 1 at the same time, and there was nothing that would tell you that this was happening. So we added features to this. We added a promiscuous mode so that the radio would decode whatever audio came in, regardless of who was speaking and whether or not you were a member of the group. We also added like a last heard listing. So here with this radio on the right, you can see complete with timestamps who is talking to whom. On the left, you see mostly amateur radio call signs. These come from an internal address book that we added. We had like tens of thousands of amateur radio call signs and first names so that when you hear someone talking on the radio, you know who you're talking to. And on the right, you see the talk groups, 3172, 50496. These are internationally repeated talk groups. They're like chat rooms, but for ham radio. And only because of this feature can you hear which chat room another user in your city is using through the same tower. These features made this the very best radio for that protocol for many years, and it only got replaced by better firmware because a separate team was sufficiently motivated to write replacement firmware from scratch with no dependencies upon the vendor firmware. And lately I've been playing around with this thing. I do film photography and film x-rays, and I'm getting into film cinema, like shooting home movies on 8mm. This is a hot shoe camera flash, and I began taking these apart in order to convert them to infrared. I would put infrared transmissive acrylic on the front, and then I could take pictures of dogs in my neighborhood bar without blinding any of the drunks or starting any fights. Along the way, I saw that these things charged by USB-C, which is great as a photographer because I don't have to bring batteries around. And with USB-C, I can always pass it to the bartender to get topped up from a cell phone charger. If you hold this button on the right, while turning the power switch on the left. The flash boots at a mode where it doesn't fire as a flash, it doesn't show you the charging screen, it does show you the model number on the LCD, and it enumerates by USB, and in USB it begins to accept firmware updates. And through that I was able to dump the firmware and begin reverse engineering it. I'm hoping to add something like a double flash so that I can get dual exposures. And today we're going to talk about how that works. We're also going to talk about where to look for if you're trying to exploit DFU. This protocol has a lot of sharp edges to it. It's very hard to get right. And there's usually at least 2 copies of this protocol with different implementations in a device that uses it. And you as the attacker get to choose which one you'd rather play with. We're going to talk about dumping firmware with it and how to make a tool targeted toward device readout. So this protocol was intended for putting new firmware into the device. Today I'm telling you how to rip the firmware out using that same protocol. The protocol itself is a USB standard, but if I were one of those people to use air quotes, I would put them around the word standard. A lot of this is very ambiguous. There are a lot of pieces in the standard where you could implement it one way or the other way, and there's no clear winner, and I can cite implementations that do it each way. There are also a lot of missing features here. There's no completely standard way to tell it the address that you would like to read or write from. So that got added as a vendor proprietary extension. Similarly, there is no way to do things like setting the wall clock time. So that got added as another extension. And there is no way to select between multiple memory spaces. So that got added as another extension. There's no way to ask the machine to reboot. So that became another extension. And these extensions were often vendor proprietary rather than standardized. So you basically need to sniff USB traffic, find the packets you don't recognize, and then interpret them to add that feature to your client. To enter device firmware update mode, there are different ways to do this, and some devices have more than one of these that work in different ways. The first thing is there will be some I/O pin. ST Microelectronics likes to call it the boot 0 pin, or BT0. You just short that to 3.3 volts. Power the chip up, and an STM32 will come in the ROM copy of the DFU bootloader. In other devices, like on this device, you have a secret button combo. So I told you that I hold this button that my index finger is on, and then I flip this switch, and it powers up in the bootloader mode. There's also support for USB alternate settings. So sometimes the computer is talking to the device. Maybe it sees mass storage, maybe it sees a serial port, and it says to it, hey, I don't want you to be mass storage anymore, I want you to be device firmware update. This used to be really popular for devices to include their own drivers. It would plug in first as a thumb drive, and then when the software runs, it tells the thumb drive to become whatever other device it wants to be. And then the final way that this can appear is it can just always be on, particularly for handheld radios or things that don't need to be in a special boot mode. They might always expose device firmware update, and you can just begin talking to them. The protocol involves descriptors. So the device will tell you that it speaks device firmware update, and that part is standardized. STMicro has a kind of standard way to tell you what buffers are available, but this is a separate list from the factual list. So a lot of the buffers that it advertises are wrong, and a lot of the buffers that are available are unadvertised. It's very important that you be able to search for them. It has these verbs that you can run. You can detach or abort a connection. Often when you do that, it will begin executing whatever program you had just downloaded. Download in the case of this protocol means to copy into the device, and upload means to copy out of the device into the host computer. It has some status bits and like a state machine that you follow. And all of the transactions occur as blocks with a 16-bit index. Who here likes Visual Basic or Lua? There's no shame in it. Hold your hand. Okay, I got it. In Visual Basic, what's the first element of an array? 1. And in C, the first element of an array is, okay, you should have said 0 as God intended, but close enough. In DFU, we don't use 0-based addressing, and we don't use 1-based addressing, we do 2-based addressing. The reason why this is done is because the 0 index is a special block, and whenever I read or write, meaning upload or download the 0 block, I'm actually exchanging a status. Now, if the 0 block is used for that, the 1 block comes next, but we can't use the 1 block or people will think that we're like the Visual Basic weirdo in the corner, and they would judge us. So instead, we do 2-based addressing. A lot of the 0 block transactions include vendor proprietary stuff. The 1 block addressing I've never actually seen. Nobody uses the 1 block for anything, and I don't know why. Now, the way that you calculate this is that the actual address that you're accessing is the base address plus 2 less than the index times the block size, except that there is no standard command to set the address. There's a non-standard one, which is like 5 bytes that you send to the 0 address, and everybody copied that from STmicro. So we kind of have a way to do that. And the protocol says that this is times the block size, but it does not say whether it is times the advertised block size or the block size of this individual transaction. And everyone does it one way or the other. The safest thing to do is to make your transactions all the advertised block size, which will be about a kilobyte. Okay, so we're going to do some math in our head. If our base address is 0800 C1000, our block size is 0x400, and our index is 3. Well, the way the math works is we take 3 minus 2, and we multiply that by 400 hex. So we're then looking at 0800 C400. And that becomes the place where we're actually doing our access. The base address setting command in some implementations will give you an error message if it's in an illegal range. And this is great because it lets you know what is available to read or write. It's also a lie because there are some addresses that are legal to set but not to read or write. So you might get a failure later on. It is also sometimes ignored. And it has an implied default value that in most implementations is the beginning of firmware, which is cool because after you scan the whole address space, you can use this to figure out where the firmware begins. This is usually embedded ARM, so the firmware usually begins somewhere near 0800 and change, but you don't always know the offset, so it's nice to be able to look for it. Now, the STmicro extensions that everybody copies, they're called DFUs, and they fill in the very basic missing commands. Setting the base address, very important to do, not a part of the standard. Erasing pages. This is such a basic thing. Like, we're talking flash memory, so if I write twice to the same word, without erasing it, I get the bitwise AND of everything I've written there between erases. But there's no standard way to erase the page, so you have to add it. They also support providing a listing of memories, which is not something that's part of the official standard, but added for STmicro and very useful to have. You want to know that both RAM and flash memory are available. You also need to know about things like OTP memory or boot ROM that are easy to overlook if you're only reverse engineering an application. It's very important to know that those exist because they can be used as free targets for shellcode. If I know that I have another bootloader in ROM and I get control of the program counter, I can jump into ROM and execute that even if I don't have any space for my own shellcode in RAM, even if RAM is not executable. Now, these extensions are not enough for things like setting the clock time or choosing which memory to program, and those extensions are handled by vendor proprietary code. The radio manufacturer will add them. The important thing to note here is that when they add those extensions, they're not staying up to date with the original code. They're forking it, because this is the embedded world. Which means that if you find any bug in any one of these implementations, particularly in a reference design, and that reference design gets forked to include the bugs, no one's ever going to get rid of those bugs until they redesign their product around the next chip. This forking also means that we have many different implementations to work with, sometimes within the same device. So STM32 chips have a DFU bootloader in ROM at 1 FFF and change. A lot of them will also add a flash application that is unique to the product being manufactured. So ST Micro has their bootloader in ROM, then the radio company adds their bootloader in flash, and the attacker gets to choose the easier target here. So if there's a bug in the ROM implementation, I will use the ROM implementation. If there is a bug in the flash implementation, I will use that one. And in some devices, I've seen 3 or even 4 separate copies of this protocol implemented, each with different bugs and edge cases. And in the ROM, you have an even worse condition because you're not able to fix this with a firmware update. You have to throw away those chips and manufacture fresh ones. And you do that periodically. Early STM32 F407 chips have very severe bugs in their DFU implementation that got fixed, but they didn't get fixed until 5 or 6 years later when all of the dice ran out and they had to manufacture new ones. So the tool that I wrote works from the Unix command line. You'll notice that I'm using Macintosh for these the screenshots. Apple has a better USB stack than Linux does, at least if you're using the libUSB library. Most of this code will also work on Linux, but we'll have specific cases that do not. The first thing that you might do is list the devices that speak this protocol. Dash lowercase L will do that. The next thing you might do is attach to it and start looking at stuff. So dash capital A means automatically connect to the one device. On a Mac, this is easy because you have no other USB devices. Not your mouse, not your camera, none of it. Here I've got the first bit of hexadecimal code. The capital H says, grab me a block and show it to me. We have a lot of reverse engineers in the audience. Who can tell me what architecture this is from, and how can you tell? This is one of those magic tricks that looks like really hard until you know the trick. So you know the trick. What is it? It is ARM, yes. Is it 32-bit ARM, or is it thumb? You're wrong. Who can say why he's wrong? Ozzy's right. Ozzy, why is it Cortex M3 running thumb code and not 32-bit wide ARM code? Right, so he says that the very first 32-bit word, it's little endian, it is 4-byte aligned, and the most significant byte is 20, which means that it's in the RAM region of a Cortex M3. And how do you know that it is, these pointers, they're odd? What does that mean to you? Thumb, right. In 32-bit ARM code, you have an even address for a pointer if it is 32-bit wide code, and you have an odd address if it is 16-bit code just 1 byte before the listed value. We can also specify an address. So here I'm saying I don't want this from Flash, I want this from the beginning of ROM, and I'm doing that by specifying the full address. And that works, and I get my hexadecimal back. I can also ask it to scan addresses for me. So here I'm telling it to do an address scan, and it first runs through all of the addresses that it expects to work. 800 and change is the flash memory on a Cortex M3, many of them. And that's valid for so many bytes. 1 FFF is mask ROM, and that's valid until 1 FFF and a half. The one beneath that is option memory space, I think. These are like OTP bits that you might burn once. And that's a related but separate region. And then the 2000 and change entry at the bottom, that's your SRAM. And it's identifying all of these regions separately by trying addresses and waiting to see whether it gets an error for specifying that address. After it quickly identifies these few, it'll sit there for about half an hour while it runs through the rest of the 32-bit address space, just trying to see if it missed anything. It probably won't come up with values there, but on some chips it does, and it's useful to know that they exist. You can also tell it that you want to upload everything that it finds in the scan, and you can tell it to exclude particular regions. So in this case, I'm telling it to leave the option bytes alone, but to grab everything else and give me a .bin file for reverse engineering. I can also dump strings. So in a USB device, you have indexed strings. It's a 1 byte index, so you can have up to 255 strings. They're all UTF-16, and they can be region encoded. So you can make a thumb drive that has a French name that is different from its English name, and the operating system can figure out which should be displayed. If you run through all of these strings, you will also find listings of some of the memory spaces in STmicro-derived code. This is useful because it sometimes tells you what type of memory a thing is. And you can know that this is code memory or this is RAM without having to guess or look at the data sheet. Our interest is in dumping this code, though, so we're very interested in bugs. We're going to talk about stability bugs, smashing the stack, logic bugs, which are often exploitable here, and null pointer dereferences, which are frustratingly hard to exploit on some architectures, but here come out very reliably exploitable. The first problem are these stability bugs. You have to care a lot about these because they will stop you in your tracks when you're doing an experiment. If you want to dump all the firmware from something and you read from the wrong address, it might crash. Wrong size, it'll crash. Anything that you do that it doesn't expect triggers a crash. But crashes can be costly here because this device has no real power switch. It has a soft power switch. And it has a 10,000 milliamp hour battery. And the only thing that battery powers when it's not flashing is like a little LCD screen. So on one of these things, if you crash it, you're not triggering a reboot. It sits there with a dumb look on its face and still tries to handle the interrupts that occur. It doesn't work well enough for you to get anything out of it, and you have to wait an entire week after disconnecting it before the battery dies and it naturally reboots. This device I have labeled because I opened it up and cut one of the power traces just to be able to quickly reboot it every time I crashed it. For smash stacking, we have all these different memories available. And even on locked devices, you sometimes have access to SRAM. So if you find the call stack within SRAM and you overwrite that with a different pointer, and then you allow it to naturally return, you have remote code execution. You put your shellcode somewhere else, you get it going. So the way that you do that is actually very direct. As Ozzy was correctly yelling out earlier, the first word is the top of the stack, and the words after that are pointers to functions. So 2002 AE8, that is the top of the stack. And if we look at that address, where that arrow is pointed to, you'll notice that every word that is lower than that point in memory, for quite a few of them, is either a null word or it is a function pointer. And those function pointers are to odd addresses, which is good because that means thumb2 code. And it's in flash memory, which is good because that's where our DFU implementation is on this device. And if we go a bit further, if we look at that address, so again, the value we see there is 0800 014F. 014F is actually that F9 byte at the very end. And that's not code, that's just like garbage between code. But what's happening here is that in thumb2, the callee saves the return pointer. So when you have a function call, it is the child and not the parent that saves the pointer. And the child does this based upon what's in the link register. And there's only one link register, and it's the child's job to save it before calling on to anything else. When the instruction at 14A is called, that branch and link to DFU enter SAP, the link register is saved pointing to the very next byte, which would be at 14E, except that it's odd, so it adds 1 to that, and that becomes the 14F. So this region of memory contains all of our return pointers, and one of these return pointers will be to the upload function that is reading a block out of the device. And at about that same alignment, maybe a word or two off from it, will be the return pointer from the download when you're copying data into the device. And that's the word that you need to clobber to get remote code execution on this. There are also exploitable logic bugs. So the STM32F407 has a CPU with this funny little restriction on it. Again, I mentioned earlier that if you have a manufacturing line and I tell you that the line needs to shut down for a security reason, you tell me to go fuck myself. It is not an easy conversation to have, and if you actually do need to shut down the line, it is nothing to be taken lightly. So everyone wants some sort of a middle compromise on this. And for the STM32F407, the compromise is that you can speak a little bit of DFU, but you are not allowed to read or write anything in memory until after you do a mass erase. When you do the mass erase, it blows away all of the contents of flash memory. It does not erase RAM. And the idea is that you no longer have access to the code in the device, so you're no longer able to make counterfeit ones. And if your only security concern is that you don't want counterfeit devices, that sounds like a reasonable compromise. The thing that they forgot in early versions of this chip is that there's also a command to detach. And there's a command to set the working address. When you detach, it executes the application at the current working address, which you are allowed to change. Which means that if you change the working address to any place in RAM that has shellcode, and then you detach, it will run that shellcode for you. That gets you remote code execution, and at that point, you can start blinking all the firmware out LEDs and catch it on an oscilloscope. This is like a little logic bug. This is not anything that anyone would notice as being corruption in a particular command or anything like that. It's just that the detach command should be restricted, and it's not. And those business logic bugs are exploitable in this protocol and are very often worth looking into. They're also very hard to spot. I don't know any code analysis tool that would have recognized that the detach command should have been special. And you can do null pointer dereferences. So raise your hands again. Who likes C? Okay, and keeping your hands up, also raise your hand if you like C only when the other guy is running it. Okay, a lot more hands. In C, the pedantic folks will tell you that a pointer and a number are different, but to a reverse engineer, they're the same thing. Addition works differently for them, but otherwise they're numbers. So when I call the malloc command in C to allocate a buffer, I get a pointer back to that buffer. And it's tradition in C that if I have not allocated that buffer, or if I'm out of memory, to return a 0. And in Unix, the way that many of us first learn how to write C, if you dereference the pointer 0, what happens? A crash, a segmentation fault. And a segmentation fault comes from an early competitor to virtual memory. And virtual memory is something that we do not have in this chip. On this chip, when you dereference 0, you get a copy of whatever memory you booted from. So I told you that flash memory was at 0800 and change, and ROM was at 1 FFF and change. Whichever of those you first booted from also exists at 0 in both locations at the same time. It's called mirroring or ghosting. And so if I have the ability to read a buffer from your code, and your code hasn't initialized that buffer yet, and that buffer is now at 0, and you tell the chip that you want a DMA transfer of so many bytes at 0 to me, what you're going to do is you're going to send me the first so many bytes of your boot memory. And that's great because your boot memory contains your bootloader, and if I have a copy of your bootloader, I can look through it for bugs, and I can look through it for decryption keys. So in this device, the Titera MD380, there is a buffer here at 0800 4AC8. And if you look at this, you can see that it begins with 2EDF whatever. And there's also this code here that takes that buffer, that XOR key, and it XORs the bytes of it against the incoming data of the block being loaded. So this is the XOR encryption key that all of the firmware is covered with. And in the Python code, all we do is have that same string, and then we XOR our stuff around it. But in order to find this string, it is really helpful to have a dump of raw protected memory. And the way we did it was with a null pointer dereference. Now, there's one complication in here, which is that Linux hates all of us and wants us to suffer. And libUSB on both Linux and Windows has a line like this. This is the Linux version. It's saying that if you're doing a control transfer, which is like, you can think of it like port 0, if this were networking, which it sort of is. If that's longer than max control buffer length, which is hard-coded to 4096, then it just returns an error for an invalid parameter. This means that on Linux, I can never read more than 4 kilobytes from my device in a given upload transfer. In a null pointer dereference, that is awful, because in a null pointer dereference, my index is ignored. Normally I would have the index minus 2 times my block size added to my base. My base is 0. My index is ignored because my buffer doesn't really exist. And so in Linux, this means I can only get 4 kilobytes at a time. So when I was first writing that exploit, It didn't work on my Linux laptop, so I moved it to a Mac desktop. And it worked on the very first try because Macs have a different USB stack. And on a Macintosh, there is no 4 kilobyte restriction. And you can read as much as you like, including 48 kilobytes, which is the entirety of that bootloader. I've complained enough about Lua and Visual Basic and Linux and similar bad technologies today. And device firmware update protocol, which is a very ugly protocol and a very incompatible one. But I hope with this project, with DFU Explorer, that I've opened it up a bit in that by using this tool, you can connect to random devices that you might find around your home. Start playing around with the buttons on them as you plug them in and see if they enumerate differently by USB. If they do, and you see the letters DFU, then you might have the firmware. One final thing that I'll warn you about is that your badge for this conference has a button on it that says DFU. If you plug your badge into your computer and you hold the DFU button and then you briefly tap the reset button, it reboots into a bootloader. And that bootloader is a bootloader. It does accept device firmware updates, but it is not the DFU protocol, and it is completely incompatible with my tooling. It will provide you with a file system mount, and you can drag and drop firmware updates into that file system. But it works by different means, and we need a different tool to explore things like that. And that's what I have for you today. Please screenshot this. The slide's taken off. There you go. Please take a photograph of that if you need a copy of the code. It went live a few hours ago. I'm sure I have some nasty bugs, but just file them in GitHub, and I'll take care of them as I get to them. And thank you kindly for your time and attention. I appreciate you listening to me ramble. Cool. To the taskmasters, do I have time for questions, or am I cut off? I do have time for questions. If you have a question, please raise your hand and jump up and down like you have to use the bathroom, and someone will run your way with a microphone, and then we can all hear you. I think we got one here on the end, unless you've already got one. Oh, no. Ryan's in charge, not me.
So what other things have you poked at, and anything fun or interesting come out of it?
Crypto wallets often use the STM32 chip and often have these same protocol issues. Lots of low volume things or high margin things. Camera equipment is a lot more expensive than the parts inside of it because camera people will pay obscene amounts of money for stuff. So it's a good target for this. Radios are a great one. And a lot of product lines in a series will use similar chips. So if you find that a chip uses something like an STM32 or whatever the LPC in that same range is, start looking at competing products until you find one with DFU enabled. And remember that as the reverse engineer, you can always jump between products until you find the one whose firmware is easily accessible, rather than having to hammer your head against your first target. Yes?
2 questions. Did you test this in Apple ecosystem DFU? And the other question is, have you tested it on any other embedded controller things that use like secure boot, or is it all just less secure chips?
Great question. I am intentionally not looking at the Apple stuff because I enjoy having all 10 of my fingers. If anyone from Apple is listening, I'm not touching your stuff. Please don't chop off my hands. In other embedded controllers, like I've mostly been going by the chip part number or by the opportunity of it enumerating itself the right way. You'll find DFU listed for like the cameras on some models of ThinkPad or all sorts of weird stuff. So keep running LSUSB-V as a habit, and eventually you'll start seeing this protocol pop up, and then you've got your opportunity. Cool. All right, I see no more questions. Thank you kindly for your time and attention. I'll be around.